Okay, let's get started. It's I don't know whether people sitting in the back can hear me. It's a long room, so might as well move to the front a little bit. It's a great pleasure to introduce the speaker of the session. Professor Rodrigo Bañuelos received his PhD from UCLA in 1984. And he has been with Purdue University since 1986. Professor Benvelos' research interests are in probability and applications to harmonic analysis and spectral theory, with emphasis on singular integrals and the geometry of the Laplacian and non-local operators, on which he has written and lectured widely. Professor Benvelos has won numerous awards and honors, including the 2004 Blackwell-Tapia Prize in Mathematics, fellows of the AMS and IMS, and the 2022 AMS Award for Distinguished Public Service. Each year, the IMS Committee on Special Lectures selects 4 to 5 medallion lectures based on research achievements in fields across the IMS subject range. This year, Rodrigo, the IMS has selected you as one of the lecturers and invites you to give a lecture titled "A Doob H process and its applications to singular integrals on ZD." Before you start, though, on behalf of the IMS, let me present you with the medallion that comes with the honor. Thank you. Congratulations.
Okay, thank you very much for the introduction. And I want to thank the IMS for giving me the opportunity to give this talk. So I'm going to speak about a problem that has been around for quite a while. It is a very, very simple problem to state, but somehow, at least to my surprise, after I learned of it, I thought, that it was a little surprising that it has been around for that long. Really, so this is a talk about one single problem, but I want to tell you a little bit about the techniques that are of use here. Can we put it on the full screen? Okay, thank you very much. So in 1978, Richard Gandhi and Nicholas Baropoulos wrote a beautiful 3-page paper in which they gave a representation for these operators, which are called the Riesz transforms. Now, the Riesz transforms are the building blocks sort of singular integrals and can be interpreted without the reference to singular integrals. So they are just given as derivatives of inverses of the Laplacian, okay? And so the Gandhi-Baropoulos representation says that if you look at Brownian motion in the upper half space, okay, which is the x-axis and the y is the vertical component, then the Riesz transform can be written as a conditional expectation of these operators with respect to a certain measure, okay, that you construct with certain initial distribution. So this representation actually was in the books, was published in 1978. And unfortunately, Gandhi and Baropoulos proved was a 3-page paper. So it's a beautiful short little paper. The proof is extremely simple. You essentially compute Green's functions, and then you use occupation time formula, and the representation comes out. But they did not give any applications. They just left it there as a formula. Nothing said, this can be used for this or that or that. So in 1984, I wrote a little paper with several observations. Okay, I call them observations now. Of course, I call them theorems then because I wanted to publish a paper. but they really were observations in some sense. My first observation is that you can define these operators, which I call T sub A's. I call them T sub A's because I was a TA, a teaching assistant. Otherwise, I would have called them RAs if I had been a research assistant. But in any case, the first observation is that you can put a matrix, transform the gradient of the Poisson semigroup, okay? Take the stochastic integral and do the same conditioning. And then you get these operators. And these operators are bounded, and they have this universal bound, independent of all the geometry of Rn, independent of anything else. So they just depend on the norm, on P, which is the maximum of P and Q, where P and Q are conjugate exponents, and the norm of the matrix A. The matrix can be, in fact, it can be a predictable process that you can put in there and construct the stochastic integral, and provided you have uniform boundedness, you still get back an operator that looks like that. The constant actually turns out to be best possible, the constant P star minus 1. This constant is Berholder. So you see, Berholder in 1984 published, well, it had not even been published, a famous paper in which he constructed, best constants in martingale transform inequalities. And so I was there at the right time. The paper had not been published, but I heard a lecture from Berholder and I immediately saw these. And the motivation for this came from a problem that Eli Stein had left open concerning the behavior of the constants in the Riesz transform. So these Riesz transforms operators have been around for a long time, have been very widely studied. Now, another observation, yes?
What's that U? Equation one, you have grad UF.
Oh, UF is the harmonic extension of the function f. So instead of using py sub f for the semigroup, I use u sub f here in the integration in the stochastic integral. Right. Now, the other observation is that if you take these matrices, which are essentially the matrix takes the last coordinate, puts it in the k coordinate, and puts a minus in the k coordinate, all right? And if you take these matrices, and I wrote for d equals 1, you just have one matrix. For d equals 2, you have 2. Then these matrices satisfy the fact that the norm is no more than 1. In fact, this is most of the time is equal to strictly less than 1, except when d equals 1. And they have this orthogonality property, which is not used, but these matrices give you the Riesz transforms, and you have this universal inequality independent of the dimension, independent of the geometry of Rn, which is not what you get when you do singular integral theory, right? Calderon-Zygmunt gives you lots of constants. And what happens is that Stein had proved that you have independence of dimension, but unfortunately he ruined the dependence on P. So my object here with this observation was to correct Stein's mishap, that you get the right dependence on the independence of dimension, the independence of the geometry with a constant depends on P, but his P was not the right behavior. He didn't have the right behavior. For example, it was big O of P goes to infinity, which already singular integral tells you that that is not correct. Okay, so this was just an observation there. Okay, now the other observation is that these objects, you can compute their kernels, right? So their kernels are computable. And these kernels include Calderon-Zygmunt operators, include, of course, Riesz transforms, second order Riesz transforms, and many others. Then there are now probably 150 papers at least using these TAs for various things. You can do them on manifolds, you can do them on vector bundles, you can do them in multipliers. I mean, they're just very, very widely used in the literature now for all sorts of applications. And I give a reference here to one recent paper that I wrote with Fabrice Baudouin, Li Chan, and Yarin Sarin. Okay, so let me now go to the problem that I want to look at, okay? So the problem that we wanted to look at here is a question that excited the interest of many analysts during the early part of the 20th century. So the question was, how does the size of a periodic function control the size of the conjugate function? So for example, very simply stated, if you take a polynomial a trigonometric polynomial and you take its conjugate, right? This is the conjugate. So the conjugate really is obtained. It's the name for the conjugate is that you take the function, you think of it as a function on the unit circle, you take the harmonic extension to the disk, then you take the conjugate harmonic extension, you take the boundary values of that, and that produces the so-called conjugate function. And the question was, if one is an LP, is the other one is also an LP, right? So the size of these functions are measured by the P norm. And the periodic case, the general periodic case, has an integral representation, all right? And Rees proved in 1923. The paper was published in 1927. So if you're ever worried that your paper that has been lingering around for a while in the referee's pile is not going to be published, so you can think of Rees, right? And this is a very famous paper. He proved the inequality. The non-periodic case also follows from the periodic case by certain conformal mapping. And of course, this is equivalent to proving, you know, that the Hilbert transform, again, the conjugate function, the Hilbert transform is bounded in LP. And this is called the Hilbert transform in the continuous case. Before the 1900, this was called the conjugate function. Why is it called the Hilbert transform? Well, even I did not know this for many years. But the reason why this is called the Hilbert transform is that Hilbert in 1907 introduced various quadratic forms, some of which are very well known to all of us, right? So this Hilbert integral where you take f of x times g of y, you divide by x plus y, integrate from 0 to 1, 0 to 1, and that gives you something that is bounded that is bounded in LP. So the P norm, take the absolute value of that integral, that is less or equal to the P norm of f times the P norm of the Q norm of g, right? So it's a quadratic form. So you can think of this object as a singular quadratic form. That's what Hilbert called it. And Hilbert actually speculated that this singular quadratic form should have the same norm as the continuous version, right? Okay, because the non-singular ones had the same norm, right? So the Hilbert integral, you look at the quadratic form in the of the integers, right? And then they have the same norm. So, okay, so Tishmarsh, Hilbert also proved that his bound for the continuous one implies the bound of this one. The following year, Tishmarsh proved to turn the Marshall-Rees proof and turn it around and first prove the discrete version. And then he concluded also by some other argument that in fact they have the same norm. So settled the issue, right? Unfortunately, the following year, Tishmarsh had to write a retraction or a correction, okay? In paragraph 4 of my paper, blah, 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 involving series and integrals, they prove that, you know, these two operators are equal, right? Have equal norm is incorrect and should be deleted. This does not affect anything else in the paper, okay? And then he went on, and at the end, he comes clean with one little fact that he already knew. Rees's proof, not only his theorem, but Rees's proof. And in fact, he modified Rees's proof, which was for continuous Hilbert transform, to the discrete Hilbert transform. So the problem then became an interesting question. Are these two norms the same? Right? Okay. And these actually had resisted the approach of Gandhi-Varopoulos, resisted all other approaches. So what I like to do is give you an outline of how one proves this theorem. Now, before I go on, there's a beautiful manuscript, a beautiful article published in the London Math Society, which is titled Manuscripts of Harry Littlewood, Marcel Rees, and Tishmarsh, where Mary Cartwright, who was the last student of Hardy, publishes letters between Marcel Rees and Hardy, and is a really delight to read because there's very personal stuff, you know, about their thinking. There was real competition between UK and London and Stockholm, okay? friendly competition, but yet sometimes not, these little disagreements. So it's this wonderful reading, and I could actually take a minute to read it, but I'll read you some of it, but I think for the purpose of moving along and finishing on time here, I will just move along, but it's highly recommended, that article. It's lots of literature. The inequality that the discrete Hilbert transform is bounded by a constant that depends only on P. Many proofs. Discrete Laplacians, even Gandhi-Varopoulos with semi-group theory with discrete Laplacians. Lots of papers on that, and there's some literature that I list there. So now, one thing that was quite difficult for many years is that they were trying to prove this without knowing the exact P norm of any of the two operators, not the discrete, not the continuous. In 1972, Picorides proved that the Hilbert transform has this norm, which is the cotangent of pi over 2p star. Again, this p star is Burkholder's constant, right? And this constant is smaller than p star minus 1, which actually follows from the observation earlier, because in one dimension, the Riesz transforms reduce to just the Hilbert transform. So already from that observation that I made, you get p star minus 1, but that's not the right constant, right? Okay, for the Riesz transforms. And what we prove with my co-author Mateusz Kwaśniewski in 2019 is that in fact the discrete Riesz transform also has the cotangent of pi over 2p star bound for the P norm, and in particular the discrete transform then is less than the P norm is less than the P norm of the continuous one, and together with Riesz then you get the equality, right? Okay. So I want to give you a little bit of an idea of how this is proved. Okay, now, however, before I do that, I would like to tell you another problem in higher dimensions that occurred a little bit later. So there's this famous paper of Calderon and Zygmunt where they began the Calderon-Zygmunt theory in 1952. And in their paper, they proved the continuity of singular integrals, which are these kernels, right? And towards the end of the paper, they make the following remark. So they consider the continuous versions, right? They have to take away the singularities, 0, because that's already infinity right there, right? But then they say the following: for d equals 1, so then they say for d, these holds, right? These bound for the discrete singular integrals also holds. For d equals 1, this remark is due to M. Riesz. The proof is due to M. Riesz exactly in the same way that he proved the general case. And what turns out, okay, is that that's true, okay. But not only that, their P norm, okay, is bounded for various general classes. So this is actually a recent paper with Mateusz Kwaśniewski and Dao-Sung Kim. For these kernels, you can actually prove that you have less than or equal, right, with constant 1 for the discrete. So this is the analog of Riesz's proof, right, in general, in higher dimensions for a specific collection of singular integrals, right? But you see, there's lots and lots of work again on discrete harmonic analysis. Okay, so Bourgain, Stein, and many people have actually studied, the classical operators of harmonic analysis, not on Rn, but on discrete setting of integers. Okay? There's a very popular thesis from which everybody who enters the subject reads of Lillian Pierce, who's an analytic number theorist at Duke, who wrote a thesis with Eli Stein that is about 400 pages. I don't think I have seen too many PhDs theses of 400 pages, but this one is really a very beautiful piece of work because it's expository and it gives you a way to enter the subject. Actually, an interesting thing is that the people who do analytic number theory, I don't, okay, actually use a lot of these techniques of computing exponential sums and so on. And those methods actually have also been tried for this particular problem, but again, without success yet. So the Riesz transforms, which extend then the Hilbert transform, actually have norm, which is exactly the same as Picorides norm. So the P star was not the right constant, right? And this was followed from a paper that I wrote again in 1995. And then in 1996, it was proved analytically anyways that this is actually the right bound for the Riesz transform, the discrete Riesz transform, which are called the Calderon-Zygmunt discrete Riesz transforms. And so the corollary then, since you know that, and you know that the continuous Hilbert transform is the same as the continuous Riesz transforms, is less than the discrete Riesz transform, and then one can actually obtain this bound with this constant that depends on dimension. So what you would like to do to solve the higher dimensional problem is to remove this constant, right? And then you will have that all of these operators, the discrete and the continuous, are all the same norm. And so it will be a generalization of that. So the conjecture is that this inequality holds. Okay. So let me tell you, so the proof uses one theorem that extends Burr-Holder's inequality, namely that if you take two martingales, two stochastic integrals, that are represented by predictable process K and H, right? And you said that N is subordinate to M if the vector Ks is less than or equal to Hs, almost surely for all S, right? And orthogonality means, okay, the quadratic forms essentially are the quadratic variation, okay, is essentially they're orthogonal, right? Orthogonal for all S, right? Okay, so that's orthogonality. So orthogonality gives you a bound which is cotangent pi over 2p star, namely the Picorides constant. And so you see, when I wrote earlier that observation that p star minus 1, I did not use the orthogonality of these matrices. So this actually gives you the bound, okay, for the continuous Riesz transforms. Now, let me quickly tell you a proof. Okay, this proof is not worth 10 cents, believe me, right? Because there are many, many proofs that are very simple now of Picorides. But I want to illustrate with this proof the argument that I will use for the discrete version. So you take the Poisson kernel, okay, you take the Poisson extension of the semigroup of the function, the harmonic extension. Then you observe, of course, that it's a boundary value problem. So as y goes to 0, you pick up f. As y goes to infinity, the function vanishes at infinity. But if you multiply by pi, y pi, right, times u times the function, you pick up the integral of the function, okay? Because the Poisson kernel pi times y converges to 1, right? Okay, so this gives you a way to write expectations in terms of integrals of functions in terms of expectations, right? Okay, so the expectation is just the harmonic extension is just the expectation of the function at x time, and then you apply the Cauchy-Riemann equations with this harmonic function h, right? And you see that these operators are actually dominated, that these two martingales are dominated in the right way. And they're orthogonal because this matrix is orthogonal, right? Okay. So H of V dot is perpendicular to V for all vectors. Okay, and so that then you apply it to these two martingales. The beauty of this is that in the harmonic case, in the one-dimensional case, the conditional expectation doesn't have any action. You get back right to the Hilbert transform of the function f. Okay? So this got the representation. So then you apply the theorem with Galois, and then you get this inequality. You multiply by x, or pi, you fix x, you multiply by pi y, and then you get Picorides theorem, right? Okay, so that's what we want to do now, but in a different setting, right? So now, so almost the same for the discrete. except you replace Brownian motion by Brownian motion conditioned to exit the upper head space through the lattice. How do you do that? You construct a harmonic function, which we call the periodic Poisson kernel, right? So you take the Poisson kernel with pole at n, the integers, and you sum over n. In one dimension only, you can write it down very, very easily. Okay, so you see these are exponential sums, right? People in analytic number theory use something which is called Weil's theory, right, to estimate exponential sums, right? Exponential sums. So H is harmonic. You take F and you construct that is now discrete, and you construct its harmonic extension in this way. U sub F equals Fn, and then you take the probabilities, right? Pn over H is the probability that you're exiting through the point n, and you sum them up, and this function is harmonic relative to the this Doob H process, which is constructed from this function H, right? And it has boundary values F. So now you crank the handle, right? And there you write your martingales, right? You write the martingale transform, right? And you get these operators, which I continue to call T sub A's, right? Starting at level Y, and you apply the theorems, right? So you get from Burkholder P star minus 1, you get from the theorem with GAN 1, cotangent pi over 2 P star. Now you have to convert these integrals into sums. Well, there they are, right? And the only difference is you have these weights. So now you have to show that if you multiply again by pi y, that this goes to 1. Well, it's some exercise, but nothing incredibly difficult, right? Right? And so when you do that, now let's do it in Rn, okay? So in any dimension, right? This actually is in any dimension, you can write down this function, but you can no longer write it explicitly. So it takes quite a bit of work to prove now, and this is the new work with Kim, that these operators again converge to an operator. They have bounds for any A with P star minus 1. They have bound cotangent pi over 2 P star for any A which has the orthogonality property. Furthermore, you can compute the kernels, and the kernels are a bit more complicated. There's an H here, there's an H here, there's an H here, right? And since we don't have a nice formula for H, it becomes a bit of a challenge now to try to determine what are these operators, which is really the key question now. Are these operators related to the discrete Hilbert transform when d equals 1, or the discrete Calderon-Zygmunt when d is bigger than 1? So, of course, the thing to try is to try the matrices that we were lucky enough last time, the first time, right, to get back the Riesz transforms. And so you write these matrices, you compute these integrals, and you manage to simplify, but not incredibly a lot. There they are, there are the kernels, right? And the question is now, are these kernels, right? So you have this for these operators, the bound cotangent for these new operators, which are called T sub HKs, right? And now they are, of course, in ZD. And the question is, do they give the Riesz transforms in higher dimensions? And in one dimension, do they give the Hilbert transform? And you know, it doesn't take very much work at all to show that they don't. Now, what takes a little bit more work is to try to determine what are these operators. Of course, a big disappointment if you want to prove the bound for discrete Hilbert transform. So you went through this, right? And you came back with these operators that have the right norm, but they don't give you what you want in order to apply it to this problem of David Hilbert. See, so here's the computation in one dimension only. In one dimension, you can compute these kernels and you see convolution with 1 over n plus this other factor, right? So these are not the Hilbert transform. Now, you can also compute the Fourier transform in a very precise way, okay? These are the discrete Fourier transforms now, of course, with very specific constants, functions that you actually have a lot of information on. And so the question is, you know, at this point, what do you do? Okay, so you came up with some operators and there's this problem, but they don't give you what you want. And well, I must say that I was stuck there for a very, very long time. Right? But you see, my colleague, Mateos, is very good at doing numerical calculations. And so he started working on these and doing numerical calculations. And he began to notice that there's some connection between these operator and the discrete Hilbert transform without this factor. Right? And the connection is, right, that you can actually write this operator as a convolution with a probability kernel. Right? The discrete Hilbert transform is the convolution of this operator, T sub h, with a probability kernel. And we did this just using computations. And lately, when we started working in higher dimensions, we actually found that you can write the Fourier transform of the discrete singular integral as a function, okay? It's a function u times the Fourier transform of this T sub h. And so now we have two proofs that you can do this theorem here, this factorization. One is the previous proof, and the new proof, which seems fairly promising for higher dimensions, is to use Buckner's theorem. Okay, so Buckner's theorem says that if you take the Fourier transform of a function, okay, that a function is the Fourier transform of a measure if it is positive definite, right? Here the function happens to be symmetric about -1/2 and half, and is 1 at 0. And so the probability, the kernel is actually a probability kernel. Now, I learned it, you know, I known Buckner's theorem for a long time, but it's not that trivial to show that something is a positive definite function. Because you know, you had to check a lot of things, right? So it's a little bit of work here, but we did that, and so there we are. So at the end, things work out in one dimension. In higher dimensions, right? So we already have all the right bounds and everything, but we come back again to operators which are not the Riesz transforms. And the question is, in higher dimensions, do we have the same factorization? So we are not able to answer that, but at least in one dimension, we were able to succeed with that problem. So let me end here, which I think I'm a little bit early. But, you know, since I'm a little bit early, so I have a few minutes, right?
Yeah. 10 minutes.
10 minutes, good. So I want to read to you a little bit of the exchange between Hardy and Marcel Riesz, okay? Which I thought maybe I wouldn't have a chance to do, but since I just gave a very general overview talk, I ended up early, and I don't certainly want to abuse your generosity for coming to this talk, but let me read a little bit. So on June 19th of 1923, Riesz wrote to Hardy and told him, I have approved that two conjugate Fourier series are at the same time in LP. My proof has nothing to do with Hausdorff-Young's inequality. Right? He left it at that. Then they continue exchanging letters about other things. And finally, on December 18 of 23, Rees wrote to a party wrote back to Rees and said the following: some months ago, you say, I have shown the two conjugate harmonic Fourier series are at the same time in LP. I want the proof. Okay, right? It italics. I want the proof. Right? So he was writing. Both I and my pupil Tishmars have tried in vain to prove it. Some attempts go close, and I feel that I probably could do it with sufficient determination. But it's not worth my time, worthwhile my time if you have done it already. As he is engaged on corresponding questions about integrals, it is of vital importance to him to have the proof of this rather fundamental theorem. So please send me A, the grand ligne de l'Adem, so that need be, I can reconstruct it without serious difficulty, or B, a complete proof. I need hardly say that I would have it. I would be delighted to get it published here. Okay, so now notice 18th of December. Okay, now Stockholm, 23rd of December. 5 days later. It's almost as fast as email, right? Voici le grand ligne de la démonstration décidérée. Excuse my French. I read French. My Spanish allows me to read French, to understand French, but I can't speak French. Okay? So Rees wrote in French, Hardy wrote in English. And then he goes through the proof. Beautifully written. His proof was beautiful theorem of the beautiful idea at the time, right? So here's what he said in his correspondence with Hardy on this letter after he wrote the proof. He wrote the proof and he gave the complete proof and he gave many applications of the theorem. But he wrote an interesting comment, and if there are any students here in the audience, I will apologize a little bit, but it's not my right, okay? He said that the idea for the proof occurred to him while walking home after he had to write an examination for a student, and as Rees says, who was not very bright. He said in the 10 questions that he wrote, there was a standard question of proving the theorem for P equals 2, which was Plancherel's theorem already at the time, right? So trivial. But then he said, it occurred to me that my student probably doesn't know Plancherel. So how is he going to prove it? So then he decided to look at P equals 4. And he noticed that if you take U plus IB, where these are the conjugate harmonic functions, and you square it, right? This gives you an analytic function. And he used Cauchy's theorem, right? And then he expanded, right? And he was able to prove P equals 4. And then, all right, so P equals any even integer. And he proved the theorem for all even integers. And by that time, Marcinkiewicz was around that gave you some interpolation theorem, and you got it for all P's. Right? So he writes his story in a very eloquent way. It's in French, I will not read it, but then, so here we are, 23rd of December. So he writes and writes and writes and writes, and then he comes to the end. So let me get to the end and we'll get to the end of the lecture. Okay. So this evoke, so here's Cartwright's writing. This evoke the following response from Hardy. 5/1/24, January 5th, 24, 18 for the 5th, letter to Stockholm, letter back, response from Hardy. Very many thanks. You supplied all that is essential. I have sent your letter to Tishmars. Most elegant and beautiful. Of course, page 2 is the real point. It is amazing that none of us should have seen it before even for p equals 4. Your student's life is not entirely without value, although I suppose he will never understand why. That's a pretty tough statement there, right? I mean, I don't particularly like to read it because these days this may not be so well appreciated, but it is part of history. Okay, so they exchanged many letters after that. On the 18th of December, 19th of January, only a few days after he received it, this letter from Rees, he presented this Rees's proof at a meeting of the London Mathematical Society. And he wrote an abstract that became very popular in subsequent work that was quoted. And according to Cartwright, Rees did not particularly appreciate that abstract. Okay. So, very interesting piece of work there. Thank you very, very much.
Thank you for the math and history behind it. Other questions for Professor Bañuelos?
In the higher dimensional case, when you get this other object, can the co-author can do some numerical work and try to figure out.
Well, in fact, we have in the paper, we have various beautiful pictures of the comparison between these three kernels: the continuous kernel, discrete Rees kernel, the probabilistic one, and the discrete one. And they are extremely close. But you see, comparing kernels is very different than comparing Fourier transform. What you would like is to compare the Fourier transform, right? Okay. So there may be, but I think, okay, so it's very difficult to compute it's very difficult to do it, I think, without some tools. And maybe the tool is Buckner's theorem again. But we need to have a very good computation for the Fourier transform of this kernel in order for us to then try to see if it is. But okay, so I guess the answer to that is yes. Numerically, it seems to indicate that this factorization is not so bad.
Any other questions?
I'm not particularly familiar, but is this kernel not easy to describe?
This kernel?
Okay, yeah.
No, not really. No,
Right.
no. I mean, no, not really. I mean, I was hoping that does it have some kind of probabilistic interpretation. I mean, it's a probabilistic kernel, but I mean, it's a kernel with non-negative, which sums to 1. Non-negative, which sums to 1, but outside of that, I don't know.
I guess the history question: what didn't Rees like about the abstract?
I'm sorry?
What didn't Rees like about the abstract?
I don't know. Perhaps the title of the presentation was on some theorems of M. Rees on conjugate functions. Maybe he didn't like that Hardy apparently did not ask him to whether he should do that or not. I don't know. But this is what Mary Cartwright says. I mean, yeah, I could read you, but she says
This is before it was published.
before it was published.
Right.
And you notice that Tishmar's papers was published, just around this before, right? 1926. Rees was published 1927. Anyways, and then the comment that I should have said in my paper that I was familiar with Professor Rees's work, not only the theorem. He would, right? I don't know. I'm not here to make trouble. Right? It's just nice to read history of how some of these things. Mathematics for me has always been kind of alive, right? I mean, it's a beautiful subject that as personalities, it is always nice to know how these individuals thought. You know, this gives a rare kind of a rare, you know, look. That's, you know, of course, now, you know, maybe all our email is public.
Let's thank the speaker.